of our inverse problems seminar. So we are very happy today to have Andrea Aspri from University of Milan, which is an expert on PDEs and inverse problems from both numerical and analytic viewpoints, which we will see today when he was talking about direct and inverse problems for elastic dislocations. So thanks so much, Andrea, for giving a talk.
So first of all, I would like to thank Knut and Katja for their kind invitation. It's really an honor to be here today. So as Knut was saying, today I'm going to talk about some works in collaboration with Elena Beretta from New York University in Abu Dhabi, Anna Mazzucato from Penn State University, Martin De Hoop from Rice University, and Ramon Lee from Penn State University. And the topic will be the identification of faults in seismology, which are described mathematically by elastic dislocations, and I will explain in a few slides what I mean for elastic dislocation. Okay, so here is the outline of my talk. In the first part, I will briefly describe the physical situation that we have in mind and that we want to describe analytically. So I will present the direct problem, and I will give you some details regarding the recent results on the elastic dislocation problem. Then in the second part, I will analyze the inverse problem, and in particular, I will give you and I will state and prove the main results that we have regarding the identification of elastic dislocation, the uniqueness results, and in the third part I will give you some very briefly, some details about the reconstruction procedure, focusing the attention on the two-dimensional setting, and the reconstruction algorithm is based on shape optimization tools, in particular on shape derivatives. Okay, so let's start from the introduction, the motivation. So the motivation is to study faults in seismology. In particular, as you can see here from this cartoon, we are interested in the so-called blind faults. So there are faults which don't have a trace on the boundary of the crust. So we don't have an explicit trace on that boundary. We can observe that there is something below the crust from the deformation of the crust, but we don't see exactly the trace of this fault. We are interested in modeling the slow dynamics of these faults between two seismic events. So this is the direct problem. And we will use the linear elasticity and an interface problem for linear elasticity. So in this case, the problem is linear, and I will explain the situation when we have the well-posed problem, in particular under suitable assumptions on the data. Then we are interested in the inverse problem, and the inverse problem in this setting is to recover both the fault geometry and at the same time also the slip, which creates the movement of the faults, from only one displacement measurement, displacement measurement. And in particular, we have a lot of data. And using the GPS arrays, for example, these are the blue spots that you can see here in the picture, or satellite interferometry data. In this case, there are the red spots in the picture. So in this case, the inverse problem, as we know, is nonlinear, and in particular is ill-posed. And we show you under suitable condition that we are able to prove that there is a uniqueness for the inverse problem, in particular, recovering the geometry and the slip field. Okay, so let's go towards the mathematical model behind. So we model the aircraft as a bounded Lipschitz domain, omega in R3. And regarding instead the faults, we represent the fault as a bounded open-oriented surface S, and this is called the elastic dislocation. And the definition of the elastic dislocation is due to Volterra and Somigliana at the turn of the previous century. And in the 70s, this definition of the elastic dislocation was applied in seismology and geophysics by Eshelby. And since we are interested in to slow dynamics, so in the interseismic regime, the interseismic period, the crust is modeled as a linear elastic isotropic medium, but inhomogeneous in a static regime. So it means that we are working with the Lamé system in the static regime. Okay, so since we know that the Earth crust is layered, so we have different materials in the crust, so we want to mimic this situation, considering a layered medium, omega. So we partition the medium into different sets dk, which are, of course, bounded and Lipschitz domain. And in each of these domain, in each of these region decay, the material is elastic, as I was telling you before. So it can be described by this four-border elastic tensor CK. And this is the definition of the four-border elastic tensor given by these two coefficients, lambda k and mu k, which are the Lamé coefficients, and we assume that they are Lipschitz. So for the well-posedness of the problem, I will explain later, we don't need the Lipschitz condition, but of course for the inverse problem and for the unique continuation properties, we need the Lipschitz continuity. And moreover, in order to have an elliptic system, we require also the strong convexity condition on these coefficients, so which is exactly the fact that mu k must be greater than 0, and this quantity, 3 lambda k plus 2 mu k, must be greater than 0. In this situation, we have that the operator, divergence of C, the symmetric part of the gradient, define exactly an elliptic system. Regarding the surface S, so the fault, we assume that, as I was telling you before, that it is Lipschitz oriented, and moreover, since we are interested in blind faults, we assume that the distance of S, the closure of S from the boundary of omega is greater than 0. So is completely embedded in the domain omega. On the fault S, we have, and this is the definition of the elastic dislocation, we have a jump of the displacement field. So the displacement field is discontinuous. So what in the literature is called the slip field, while we assume that the traction is continuous across S. And then I will give you some details, recent results due to Liu, Deng, and Meng regarding the fact that you can consider also the case where the traction as a jump across the surface S. But of course, so you can generalize also this condition. In particular, we are interested in the fact that the traction is continuous because we want to mimic the slip of the surface. If you consider the case where the traction is not continuous, you have an opening of the surface. So it means that there is something which is intruding inside the surface, creating a sort of hole. It could be, for example, magma, or could be water, or something like that. So we are not interested in this case. So this is the reason why we consider the case of traction continuous across the S. But of course, you can generalize mathematically speaking. The boundary of omega is split into two parts. So we have one part, the buried part, the subsurface part, which is represented by sigma, and the other part, which is the part where we have the contact between the earth crust and the air. Regarding the boundary conditions on the omega, we have in the buried part, we assume that we have displacement-free condition, so we have homogeneous Dirichlet condition. On the other part, instead, we assume that we have homogeneous normal boundary conditions, so the traction is free in that sense. So there are no forces acting on that part of the domain. Okay, so this is a cartoon, a cross-section of the situation that we have in mind that we want to describe mathematically. So we have a domain omega, we have the blue part of the boundary of this domain represents exactly the part where we are prescribing homogeneous Dirichlet boundary conditions. On the other part, instead on the upper part, we have homogeneous Neumann condition. Regarding the inverse problem, we have that with capital theta, we represent exactly the acquisition surface for the inverse problem, where we can have the measurements of the displacement, okay, only on a portion of the boundary. And we have that the domain is layered, as in this case, for example, with different elastic materials. And just to note that the surface S can cross several layers, so must not be completely contained in one layer. Could cross several layers. Okay, so what is the mathematical problem behind is the following one, is a boundary value interface problem. And I will explain in detail what we have in mind. So we have in the first part, the Lamé system, so the divergence of C grad U, grad H represents exactly the symmetric part of the gradient in omega minus the surface S. On the boundary of the domain omega, as I was telling you before, we have on one part, we have homogeneous Neumann conditions, so traction free. On the other part, instead, we have homogeneous Dirichlet boundary conditions. While on the surface S, we have a jump of the surface, or a jump of the displacement field, which is represented by G, while we have continuity of the tractions on that part. Okay, so in this case, with this notation, we represent exactly the jump across S in the sense that we are considering the non-tangential limits across S. Okay. So this is the mathematical model. Of course, for the direct problem, the input data are represented by the Lamé tensor C, the fault surface S, and the displacement jump G. In the literature, in the geophysical literature, sometimes it is called Burger's vector. Okay, and of course, this is the simplest case that you can consider, and of course you can add some other boundary conditions. For example, you can substitute on the boundary of omega, and as I was telling you before, you can consider also the case where you don't have the continuity of the tractions on S, but you can have also a jump on the traction. Okay, so it is you can generalize this model as you want, as you prefer. Okay, so regarding G, because this is the main point, we assume that G can be oriented in any direction. So G can be tangential, normal, or oblique. In the case of faults, G is usually tangential. So from the physical point of view and the geophysical point of view, they are interested in the tangential components of G in particular. So these are the situations, for example, that you can have in geophysics. So these movements of the two surfaces. And the region of S where G is non-zero is called a dislocation patch. Okay, usually in this, this is the way to call G to call the region where G is non-zero. Okay, so what about this problem? There are known results. In particular, there is a classical setting, and this classical setting is due to Okada, who worked on this problem in around 1994, and he considered the case of, for the problem, a homogeneous elastic alpha space. So he worked with alpha spaces and the homogeneous case, always isotropic, of course. And he considered also the case of Volterra dislocation. So it means that in this case, the slip field is constant across S. And in particular, he studied the case of a fault with a rectangle geometry. Why did he consider this case? Because in this case, we are able, of course, to transform the previous differential problem into an integral problem, in particular using single double layer potentials, in particular in this case, double layer potentials, and representing the solution as a double layer potential. And in this setting, we can represent the solution in this way as a double layer potential, where we have that everything is known, because in particular for the Neumann problem, the Green's function of the problem is known because was computed by Milan in the 50s in particular. And so it means that everything in this integral is known. The Neumann function G is constant, C is constant, S is a rectangle, so you can compute explicitly the solution of the problem. You can also consider a generalization, and in the case where G is not constant, and in this case we speak about Somiliana dislocation. So when we speak about Somiliana dislocation, it means only that G is not constant across S. Okay, these kind of results, and in particular this problem, the interest in this problem arose, mathematically speaking, around 2009-2010 by Volkov, because he generalized some of the results of Okada, considering the case of constant elastic coefficients but with the general fault S, so not anymore a rectangle, contained in a rectangle, in this case the fault S, and a non-constant slip field G, so Somiliana dislocations in this case, where G is assumed to be in a subset of H half. And there are a lot of results, both from the theoretical, from uniqueness results, stability results due to Volkov and Tricky, also some reconstruction algorithms. And so anyway, we are interested in the direct problem. So in this setting, they were able to prove the well-posedness of the problem in a variational sense. With Elena Beretta, Anna Mazzucato, and Martin de Hoop, we were interested in trying to generalize these kind of results, and in particular to the case of Lipschitz elastic coefficients, and general S, in particular, a surface with a general geometry, and G in H half. And we discovered in this case that you cannot get a solution in H1, and I will explain why in a few seconds in general. And but you can get only a global distributional solution. Using, in this case, we can use, and don't give you the details, but weighted subway spaces, because in this case we are still in the alpha spaces, so we can work with weighted subway spaces, duality and interpolation arguments, okay, techniques. So these are the results. Why we get only global distributional solution? Because in the case where G is in H half, and if you assume that the support of G is the closure of S, and this is a condition that you need in the inverse problem to solve the inverse problem, because of course you can have information about the surface where there is something which is acting across the surface, so in particular G is different from 0. Then computing again the solution given by Okada, we discovered that, in general, the solution may develop singularities near the edges of the fault. So in such a way that the solution is not in H1 locally, in R3. This is the example that we used. This is the alpha space. So we have the surface is a rectangle, exactly the case considered studied by Okada. And with this vector field, the Burgers vector G, and in this case, you can see that there are logarithmic singularities on the vertices of this rectangle in such a way that the solution is not in H1. So you can only have solution in general in H1 minus epsilon locally for epsilon greater than 0. Of course, this is not a physical situation, because you have that the solution, not the gradient, but the solution of the problem is damp. And of course, this loss of legality makes the solution unphysical in some context, of course. Okay, so once we had these kind of results, we asked what could we say in order to restore the variational setting for the direct problem in order to get a variational solution of the problem, and of course generalizing also the inverse problem. And we saw that in applications, instead, we don't have that the fault, not an entire fault is active, but only a patch of the fault is active at one time. So it means that the support of G is compactly contained in S, but of course for the inverse problem and for solving the inverse problem, we need to assume that the support of G is the closure of S. So we discovered that the functional setting where to study this problem in order to restore the variational solution for the direct problem is exactly a subset of H half defined by Jans-Magenes and sequentially studied by Tartar, which is the space H half 0, 0, that is of the function in H half such that we have a control in terms of the distance from the boundary of the surface of U. In particular, we have that the ratio, we need that the ratio between the U and the square root of the distance from the boundary of the surface S should be in L2. Of course, we can endow this functional set space with the natural norm. Well, in this case, using this kind of functional setting, we are able to restore, as I was saying, the variational solution of the problem to find a solution in H1. Why? Because in this setting, once we are working in H half 0, 0, we can close the surface S into a Lipschitz surface gamma, so we can close the surface. Because in this setting, in this functional setting, we have that the extension binds 0 and the restriction now are bounded operators between these two functional settings, okay? H half 0, 0 and H half of gamma. But we have in particular that the support of G can be, again, the closure of S, because we have that G must be 0 in the trace sense only on the boundary of S. So using the previous, the space H half 0, 0. So it means that given a function G in H half 0, 0, we can define an extension of this function, getting G tilde in H half of gamma, so the closure, the closed surface, Lipschitz surface gamma, in such a way that G tilde is exactly equal to G in S and is 0 outside. Okay, so now the weak formulation of the problem is the following one, is exactly the same as before, but using the right functional settings. And in this case, we are able to prove that there is a solution in H1 sigma. In this case, we represented the classical functional setting where we have the trace of the solution 0 on some part of the boundary, so in particular on sigma. And this is the result that in fact we get. There exists a unique weak solution U in H1 of the previous problem. And the way to prove this result is the proof is based on the interface gamma. So we close the surface S using the fact that we can extend our data G to a data G tilde, which is 0 outside S. But of course, the proof is independent of the choice of gamma. And we can get this result using more or less the idea is to find a potential and a non-potential using Dirichlet-Neumann map or Neumann to Dirichlet map on the surface S. And the way to get exactly this unknown potential is to identify this unknown potential using the knowledge of G on S. I don't give you the details because it's not is something classical, I would say, because it comes from some of the works of Agranovich, and so it's something classical. The other way, there are other ways, in particular, showed in the literature, in the geophysics literature, to get the well-posedness of this problem using the Lax-Milgram theorem and using suitable lift of G. So we rewrite the problem as a source problem, and then you can get exactly the same result. So for the direct problem, as I was telling you before, we don't need the Lipschitz continuity of of the elastic tensor C, we need only the fact that C is in L infinity, so we can consider in general also the case where C is anisotropic, so it's not, so the result is quite Okay, so there are some extensions, as I was telling you before, regarding this problem, considered by Yao Liu Meng in 2024 regarding this problem and the well-posedness of the direct problem. And they consider the case of general fault S, open or closed, directly closed, a closed surface, but with corners and non-constant jump functions. And in particular, they studied also the case where the tractions are not continuous across S. So they have also a discontinuity in the traction field. And again, they are able to prove a well-posedness result in a variational framework using these corner singularities and in making use of weighted isobel spaces and microlocal analysis. Okay. And okay, so let's go towards instead the analysis of the inverse problem. So as I told you before, the main idea is to reconstruct both the geometry of the surface S and the slip field acting on the surface from one boundary displacement measurement. So in general, we can consider more measurements, but we are interested in one in this case. So what are the assumptions? We assume that the data are assigned, if you remember the cartoon that I showed you before at the cross section, the data are assigned on an open subset of a portion of the boundary of omega. We have only one single measurement, and we assume, in general, we can assume that the elasticity tensor could be anisotropic, but we need, of course, conditions with ensure unique continuation properties, of course. For example, the orthotropic case in 2D. And so there are some results in the literature regarding uniqueness. So there are papers of Volkov for planar photo reconstructions and also the polyhedral surfaces with corners, for example, considered by Liu and Meng in 2024. And now I will show you our results, our result, uniqueness results. So this is the cartoon that I showed you before. So we have the acquisition surface on this part of the domain where we have non-boundary conditions. And this is the result. So let us assume that we have two surfaces, S1 and S2, which are open-bounded Lipschitz surfaces, which are completely contained in omega, and that they are graphed with respect to a fixed coordinate system. Then, if we assume that the GI is in H alpha 0, 0, and it is bounded, and the support of GI is the closure of S, Si, then we have that if the displacement is equal on the acquisition surface where we can collect the measurements, then we have that S1 is equal to S2 and G1 is equal to G2. So we are able to recover uniquely both the geometry and the slip field acting across the surface. For example, of surfaces, we can consider unions of rectangles, either oblique or vertical or horizontal also. And the case, this is a general result that we get in the sense that the geometric conditions are not restrictive from geophysical point of view. So they are quite general in this setting. So this is the result contained in this paper. Dislocations in a layer elastic medium and with application to fault detection appeared in 2023. And so now I will give you just a little bit, very briefly, the idea of the proof. So we start from considering the difference between the two solutions U1 and U2, which we call the W, in omega minus the closure of the union of the two surfaces. Then we know that on the acquisition manifold, U1 and U2 are equal, so it means that the difference is 0. By construction in the problem, we know that the U1 and U2 must satisfy a homogeneous Neumann condition on that part on the boundary. So we have that in particular on the acquisition surface. Also W as a homogeneous Neumann condition. And moreover, we know that in omega minus the closure of the union of S1 and S2, U1 and U2 are solution of the Lamier system. So in particular, W is a solution of that system. So using uniqueness result for the Cauchy problem proved by Morassi and Rosset and the unique continuation properties due to Ling, Nakamura, Wang, we find immediately that W is equal to 0 in the interconnected component G, that we call G, of omega minus the closure of the union of S1 and S2, which contains, of course, the acquisition manifold and the acquisition surface. Now, in order to prove the result, we need to distinguish two cases. The first one is the case where the complement of the union of S1 and S2 is path connected, and then I will show you in a few seconds a picture, so I will give you the idea of the two situations that we can have. While we can consider the case, and then we need to consider the case where the complement of the union of S1 and S2 is not path connected. So more or less, these what is the situation is this one. So more or less. So the polyhedron that you see is exactly our domain omega. Inside we have these two surfaces, S1 and S2. So we have two only with the assumptions that we made about the graphs. The fact that S1 and S2 are graphs with respect to a fixed coordinate system, we have that these two possible situations. So this case where the closure of the union of S1 and S2 is path connected, and instead this one where we don't they are not path connected, because in this case the two surfaces are closing. So we have this component inside where that we cannot reach from outside directly without crossing the two surfaces S1 or S2. Okay, so these are the two cases that we can have with in our assumptions, using our assumptions. So let's start from the first situation. The first situation is really simple to prove that S1 is equal, must be equal to S2 and G1 is equal to G2. Because in this case, since the closure of S1 is different from the closure of S2, as you saw from the picture, we can take a point, for example, to the closure of S1, which doesn't belong to the closure of S2. Then we can construct around this point a ball of a suitable radius r, which does not intersect S2. Hence, by definition, we have that W is equal to 0, because you need to remember that W is 0 in the connected component. So the jump of W is 0 on S1 intersect this ball, the R, but by definition, the jump of W is equal on S1 is equal exactly to the jump of U1, because U2 is continuous across S1. And but the jump of U1 by definition is exactly equal to G1. And this is a contradiction because we are assuming that the support of G1 is should be exactly the closure of S1. So instead we get that G1 is equal to 0 on an open set of S1. Of course, we can repeat the same argument, switching the role of S1 and S2. So finally, we get that the closure of S1 should be exactly the closure of S2. And we get exactly the same jump for W on S1 and S2, which means that using the fact that on S1 we have only the jump of U1 and on S2 we have only the jump of U2, we get exactly that the jump of U1 is equal to the jump of U2, exactly what we wanted to prove. So G1 is equal to G2. The second case is more involved in the sense that we have a connected component D, just to show you before exactly this ball, for example, this is the connected component D, such that the the boundary of D is contained in the closure of the union of S1 and S2. So we can assume without loss of generality that exactly the boundary of D is exactly the closure of S1 and S union the closure of S2, because if we have other components inside, then we have the union of these two situations here. So something like that plus some other parts, for example, like this situation here. Okay, so now, if you assume exactly the situation that I showed you before, that, for example, we have a ball, okay, so the connected component D is the ball, from the interface conditions and boundary conditions, we have that if we code with W minus exactly W restricted to D, so to the ball, inside the ball, we have exactly this problem to solve. So W minus, of course, solves the elasticity, the laminated system. And on the boundary of D, using the interface condition and the fact that the tractions are continuous across the surface S, so in particular across, in this case, D, we have that the homogeneous normal boundary condition. So we can solve this problem and show that W minus should be an infinitesimal rigid motion. So it has exactly this expression where A is a matrix, is a skew matrix, and C is a vector in R3. So now the second part of the proof is to show that A and C should be exactly equal to 0. So W minus should be 0. So it means that W is 0 everywhere, and we get a contradiction. So this is more or less the point. And how can we get that? So the key point is exactly the fact that the GI are in H half 0, 0. So it means that the GI are 0 in the trace sense on the boundary of SI. So for example, in this situation here, I'm sorry, we have that the GI are 0 on this on the circle connected to the two balls, S1 and S2, half ball, S1 and S2. On that part, so it is 0 on a curve in this way, and so using this fact, we are able to prove that W minus is 0 along. So we know that W minus is 0 along this curve C, but here we get the contradiction because the kernel of a non-trivial infinitesimal rigid motion is a line, while we have that C is a closed curve. So it means that W minus should be or must be 0 in D in particular, because we cannot get an infinitesimal rigid motion, or in particular we can get the case where is exactly equal to 0. So it means that W is equal to 0 in omega, and by the uniqueness of solution, we get that S1 should be equal to S2, and G1 should be equal to G2. Okay, so this is the more or less the idea to get the proof. Of course, there are other results that we need to prove, but this is the idea behind. So once we get these results, the idea was, okay, let's try to implement a reconstruction algorithm. And since we are interested in the interseismic period, so we are considering small movements of these surfaces and the small changes for also the slip field acting on the surface S. Let's try to implement a shape derivative algorithm. So the goal is to derive a distributed shape derivative that describes how the solution of the forward problem is changing if we consider infinitesimal perturbation of the first surface S and the slip field G. Okay, so in order to describe the situation of an infinitesimal perturbations, or a perturbation of the problem, we define a smooth vector field U, which has compact support in omega, which contains, of course, the support S, because we want to move force S. And the same, we do the same. We define a function H in H half 0, 0, which will be the perturbation of the slip field G. So the situation that we have in mind is exactly this one. So we define the map fit T, which is exactly the identity plus TU, where T is a parameter belonging to the interval 0, 1. And we consider the perturbation through this map of S that we call ST, and with GT we denote exactly the perturbation of the slip field G using H, okay, the perturbation H. Okay, so the goal is to study the evolution of the solution of the forward problem that now we call the UT because it depends on T, with perturbed fault ST and the slip GT. ST varies in this interval. Okay, in order to derive the shape derivative, because we are doing a shape derivative in this case because we want to see how changes the solution with respect to t, the parameter t. So in order to get the shape derivative, the key ingredient is to derive the material derivative, which is defined exactly the derivative of ut with respect to the parameter t, okay, and show that this is a solution of a certain variational problem. I will give you only the expression of the shape derivative of the functional that we will consider. So for other details, I recommend to read the paper. So in this case, we want to utilize U dot to compute the shape derivative, and in particular, the misfit functional that we consider and for which we want to compute the shape derivative is exactly the classical misfit functional, where we have ut, the solution of the direct problem, and um, the measured data on the acquisition manifold, on the acquisition surface, okay, theta. Okay, so then the shape derivative is exactly the derivative with respect to the parameter t of this functional. And okay, so we want to use the knowledge of this shape derivative that I will show you in the next slide, in order to write an iterative reconstruction algorithm via descent algorithm. So the idea is to find U and H, so the perturbation, which maximizes the shape derivative. Okay, this quantity here. Okay, so if U is the solution of the dislocation problem, one can prove that the shape derivative has exactly this form here, where you see that is appearing the material derivative. So you can rewrite this problem. Of course, it is classical using a second problem, which is the adjoint problem. So you can define a solution, a function W, which is a solution of the adjoint problem, which is exactly the problem which takes into account the difference U minus UM on the boundary of the acquisition manifold. So you can rewrite this problem here in this term. And this is called distributed shape derivative because, as you can see, it appears in this part more or less because it appears from the fact that we are considering a perturbation also of G, that there are only integrals in this case on the domain omega minus S. So we don't have boundary terms apart this one, okay? But if you consider that the H is equal to 0, so if you are interested in only perturbation of the surface, not on G, you get exactly an integral on the domain omega. So this is what is called in the literature distributed shape derivative. Okay, so this is the expression that you can get once you get the explicit expression of the material derivative. So when once you compute the you can give U dot is the solution of a particular differential problem, and in particular, if you use the solution that you get, you can rewrite exactly the shape derivative in using the primal and the adjoint states U and W, this way. So this is the complete expression of the shape derivative, where you have that du is the Jacobian of the deformation map U, and the tensor B appearing here is the fact that we don't have constant elasticity parameters, but in this case we are considering the fact they are Lipschitz. So we have something which is a Lipschitz function, so they are varying inside our domain. So this is the definition of B. In general, this B does not satisfy exactly the same symmetries of C, of the elastic tensor C, and in general is we don't have these. We are not lucky. And once we get exactly this expression of the shape derivative, we can implement some reconstruction. So we can implement the reconstruction procedure. Before doing that, we need, of course, to show and to get the results for the forward problem. And in particular, we solve the forward problem using a discontinuous Galerkin method, using piecewise linear elements. This is, as I was telling you, we are able to implement the result into D, so into two-dimensional setting. Of course, we can do also in the three-dimensional setting, but the situation is much more involved, numerically speaking. And so in our setting, and what I will show you later is related to this setting here, geometrical setting. So we have the square, minus 1, 1. The elastic dislocation is given by this horizontal segment, minus 0.4, 0.4. On the boundary of our omega, we have, on this part, we need to assume, numerically speaking, in order to get a stable algorithm, that the acquisition manifold is not only this part, but we need to assume that is larger, because otherwise, the algorithm is not really stable. So we need to assume that on three sides of this square we have measurements. Okay, so we assume that the homogeneous Dirichlet boundary conditions on this part, while we assume homogeneous normal boundary conditions on these three sides of the square. Right? And okay, so I told you everything. So the measurement is on these three sides. Okay, so this is an example of the solution that we can get using the discontinuous Galerkin method. So in this case, we are using with the slip field G 50 and 20. And in this case, I'm giving you the solution, of course, for G, which is not compactly contained, because we made the numerical test both in the case where we have when G is compactly contained, for which we have the results that I showed you before regarding the shape derivative, but also in the case where the slip field is constant across the surface. Okay. And okay, for the reconstruction algorithm, more or less we use a reconstruction algorithm which was implemented by Beretta, Micheletti, Perotto, Santa Cesaria for the electrical impedance tomography, where they considered the case of polygons. They were interested in the reconstruction of polygons. And in this case, in our case, we can do the same. So we can think that the elastic dislocation is is one side of the polygon. So we can more or less repeat the same algorithm. Of course, in our setting, the situation is more involved because we are considering the case of systems. So we are working with the elastic system. So the algorithm is more or less the same. So we update only the vertices of the elastic dislocation, where we have the elastic dislocation using the shape derivative. And in particular, in this case, the standard way to solve this problem is to find a steepest descent algorithm. So we need to identify U. In this way, in this case, in order to get an algorithm which is in particular not particularly expensive from the computational point of view, we assume that U is a a linear element of a coarse mesh containing these vertices pk, okay, the vertex, I'm sorry, this is vk, not pk, okay. And we can repeat exactly this procedure of updating these vertices going in the direction of indicated by the shift derivative once a predefined tolerance is reached and or a maximum number of iterations is reached. Okay. And in all the tests that I showed you later, we have that the alpha is exactly this this value. So these are the results. Let's start from an horizontal dislocation. And the first result that I show you is exactly the case where G is a constant slip field. So we don't have, we cannot cover with our theory the case of the constant slip field because we saw that for the shift derivative, the results also in the case where we have G compactly contained in S, but we tried in any way to implement something also for the case of a constant slip field. And since we have the singularities at the vertices, in particular the endpoints of this segment, we expect that the reconstructions are better than the case of compactly contained slip field. And in fact, this is the case of, it is a good reconstruction with 0.5% of noise adding to the measurements. This is the case instead, okay, the case of an oblique dislocation. So we change only the position of the dislocation, again with a constant slip field. Then we consider the case of G compactly supported on S. And in this case, as we expected, in fact, the solution is less precise, computationally speaking. So you see that in the blue one is the reconstruction that you get. In red, instead, you have the true dislocation. So you see that it's less precise than the case of constant slip field, more or less with the same noise added in the measurements. And this is the case of the oblique dislocation. As before, we get a good result, but less precise than the case of constant slip field. And then we tried also the case where instead of considering the measurements on these three sides of the square, we consider the measurements only on this side. And as you can see from here, the reconstructions are not good because in this case we have the measurements only on one side and the algorithm is not particularly stable. Okay. And this is the case of, in particular, in the case where we considering when we consider compactly supported slip field. Okay, so this is more or less all. This is a summary of what we did. So we study the well-posedness of the forward problem for the elastic dislocations in a variational framework using the non-constant slip field G in H alpha 0, and in particular we saw that the results also in the case where C is in L infinity, also possibly anisotropic. We proved the result of uniqueness for the inverse problem, both for the reconstruction of the fault geometry S and the slip field G, and also showed a reconstruction algorithm which works in a particular setting, I would say, probably not in the geophysical setting. I need to say that. And but we show the results only in the two-dimensional setting. We can work for the three-dimensional setting and probably doing something else in order to improve the stability of the algorithm. So this is all, and I want to thank you for your attention. Thanks.
Great. Thanks so much for a very nice talk, Andrea. So the floor is open for questions. So anyone have questions, please unmute yourself.
May I ask some questions?
Yeah.
Yeah. So concerning, I'm curious about your numeric test. For example, if you go one of the picture like test 1A, it looks to me your interface is look to be like straight lines. Are they right in your numeric test?
Yes, in this case, yes. In this case, yes, they are straight
So
lines.
you
Yes.
didn't consider really the shapes of the interface.
No, we didn't consider the case. No, you can do with yes, of course, with rectangles or something like that is more involved. The situation. So of course,
Okay.
but of course you can do it. Yeah.
Yeah, because in this setting you might simplify it in your deviation for the shape derivative. If it's just
Yeah, but
it looks like to me like just some rotation of the interface. There is no change. Oh, maybe there is change in the shape, but okay.
Yes, but you can do also if you consider, for example, the union of rectangles.
Okay.
The union in this case of straight lines you can do anyway, so you get a good results because more or less you are restricting the attention. In that case, the result will be similar to the one obtained by Beretta, Micheletti, Perotto, Santa Cesaria for polygons. So they are able to reconstruct polygons.
Okay.
So indeed, I would expect that you are able to do that anyway. So.
Okay. The second question.
More or less, the algorithm is based on the same idea. So the algorithm is not new. So it's based on that idea. So they are able to reconstruct the polygon. Probably you don't get exactly the good results they get because in this case you are considering an interface problem. But I'm confident that you can get something.
From now to have a second question, just short one. So when you change the shape somehow, because you are using DG discretization on the ground, I assume that do you need to update the shape of the triangles or something? And if you rotate too much, will be the triangles get bad in shape. This might influence your reconstruction and so on.
Yes, exactly. But in fact, we are updating also the every vertex of the partition.
Okay.
Of course, the triangles. Yes.
Yeah. Okay. Thank you.
You are.
I have two questions. The first one is about the measurement noise. Do your theorems say or imply that if the noise changes a little bit, if the actual measurement should have been close to what you got out of your sensors, the solution that you would derive in that alternative problem would be close in some way to the one that you got from the measurements that you received?
We expect, but we don't have a proof of that. Or the stability of the algorithm regarding to the noise, no, we don't have a proof of that.
Okay, but you think it might be provable?
Yes, of course, we expect, of course.
The other one is, how do you formalize the situation where you have, you believe that there are a lot of faults in a certain region, and you don't know which one is slipping, and if it's slipped, did it also change its geometry, extend it a little bit? Does that enter into your formulation somehow, or could it?
Mathematically speaking, you can do it, but I need to say that I don't know how to solve this kind of problem, of course. So the result is true in the sense that probably if you have some strange situation, no, probably it's not covered by our theorem from the analytical point of view, the uniqueness result. But I don't know. I don't have an answer to that. So probably if this, I would say that probably if the situation, so you have some particular intersection between these faults, so I don't think probably that our theorem will cover the results. So I'm not sure about that. So I know that there are situations in seismology, with a lot of faults in a region. So yeah.
Maybe
I don't have an answer. So
yeah, maybe it's a direction to move in to make it more geophysically realistic.
Yeah.
Thank you.
Thank you. You're welcome.
Any other questions for Andrea? So I was wondering a little bit, so from the uniqueness you need a very, there's a small acquisition geometry, is that so? But while from stability, you saw that you need some sort of large acquisition geometry. Is it somehow possible to understand the stability depending on the acquisition?
Yeah, yes, of course. This is one of the topic that we wanted to address. We are not working on that now, but yes, this was the idea regarding the stability also. There are some results, of course, about the stability, but not in this setting. So of course, it is interesting to do that, but so far we didn't do it. But of course, in principle, it's possible. Probably, I don't know, probably we need to introduce some other restriction on the data, probably on our data, probably or something like that to get something reasonable, probably.
Yeah. Thanks. Any other questions? Otherwise, I think let's thank the speaker once again for a very nice talk, very many interesting features, and thanks to the audience for coming.
Thank you so much.